Hey everybody, welcome to the video that I've honestly been working on for quite a while. So, back in May of last year, I volunteered to start early on the senior capstone design project of my mechanical engineering degree here at college. So, I got placed on a team of me and one other student, the goal being to take a existing Stuart platform design. I'll put a picture up here so you can see what I'm talking about, and make it so it can use a camera and track a ball in space and balance it. So you can throw a ball on the plate, it'll catch it. You can move it around in figure eights. It's all pretty cool stuff. But we had like instruction sets and pre-existing code, so we just had to get it working and improve on it a bit. So it's all great and good. So we were starting this about May, and my teammate had already done some work on this project. So he took over kind of wrapping that up, getting the code to work with the hardware. I took over the second half of the design project. So the original plan was take our original robot, get it working, and then make some modifications, improvements, etc. And that would be our second semester of work. Well, our idea was this is a senior project of a whole 4-year design and engineering program. We should go big or go home. That's what I was thinking. So I presented a pretty large project. I presented a 6-axis robot arm that would be able to do exactly what the original 3-axis Stuart platform could do, but do it faster, have more capacity, and greater reach. So my original presentation looked like this. This design, you can see, is loosely based on a existing design. If you've seen the game Portal, you'll know that they have what they call panels. They make it so you can reconfigure an entire room with software. We're doing this very similar thing. We're trying to move a square panel in 3D space, so I thought this is a very apt design, and it's kind of a cool little Easter egg, I guess. So with that, we presented this plan, got approval, and from there it was mainly just we just had to design the thing and make it work. That's obviously the hardest part. So since then, I've spent about 340 hours on this. Designing, building. About a third of that has been just fabrication. That's running the 3D printer and doing all the cutting and fitting, and especially soldering. There's been quite a lot of that. So here's the part that I'm sure you've all been waiting for. See actually what I've been doing. So this is the control system. This is almost all of the electronics that we're using. There's very little actually out on the actual machine itself. Everything's here. So let me give you a quick tour. On the front I/O, sort of, you've got two 750 watt power supplies. These are standardized server power supplies. They make it so that we can get enough energy into this without too much concern, as well as they're on sale. So that's great. So obviously this is 1500 watts total capacity. We might be using all of that, we might not. We just want to have enough overhead for the motors so we can go fast. Just up from that, we've got our air outtake. It's a pretty closed system, so every bit of air that's pulled in through the power supplies goes right back out through this fan. We've got a DVI cable. This is for transmitting the encoder data to and from the motors, as well as a external USB host, so that we can use like a controller or plug in a USB camera. Pretty much whatever we would want to put over USB, we can transmit over this cable. As a side note, we chose DVI because, as you can see, it's got lots of pins. There's focus there. Yeah. Lots of pins, and it's a shielded, twisted pair cable, so we get very little noise in the signal. Which is important because right beside it we've got all 6 of the 3-pin cables for the motors. Obviously these are going to have a lot of energy running through them, so we don't want to have too much interference with any of our other critical data. So these are all 3-pin. We've got another single ground pin which connects to all the shields. We're just trying to maintain a pretty high level of shielding throughout this electrical design. We've got power switch. This is wired directly into the power supplies to just turn those on so we don't have to be unplugging anything. We've got Ethernet for communication with the computer or with the network. We went with Ethernet because I have familiarity with running machines with UDP protocols over Ethernet, as well as it's just a pretty dandy connection, pretty fast. And then that goes directly into our controller. You can kind of see it here. Yeah. So we've got a Teensy 4.1. It is one of the fastest microcontrollers we could get. Base clock of 600 megahertz. We're not going to be able to overclock this because we don't have the space for cooling. But the biggest things is it has support for native Ethernet, as well as CAN bus, send and receive, which is important because this is our transceiver chip that allows us to talk to the O drives. We've got 3, you can kind of see them in here, 3 24 volt O drives, version 3.6. Each one drives 2 motors. You can see 2 cables each, with 1 cable out here to the power resistors for braking. These are connected up in parallel to the power supply. Each one gets 12 volts, split out of both of the power supplies, with plenty of bridging just to make sure we get even power distribution between everything. And as you can see, this is pretty compact. It's not a big package. The reason for that is we wanted to, obviously you don't want to have a sprawling mess of wires, but we wanted to put this inside of a small size ammo can, partially for shielding, partially just because I had some on hand, so I thought, this is fantastic. Might as well use them. So obviously this is very compact, very tight. It's definitely been a challenge to get it all fit in there. Next up is the actual machine. This is what 3 semesters of work will get you. You can see we've got our 6 cable shielded motor wires, the shielding all connected up right there. Got our DVI cable, dual power cords for redundancy, as well as we don't want to overload the cables. Got 2 of them. Then on the actual machine, you can see there's a lot going on here, but it's not going to be too complicated. See, we've got 1, 2, 3, 4, 5, 6 motors. And each one of them is connected directly to a 60-to-1 cycloidal gearbox, which I designed up, and so far they've been working pretty good. They're fully 3D printed, and I'm actually amazed at how smooth they are. I've got lots of bearings in them, and look at that. It's just really smooth. So smooth that it barely holds itself up under no power, just with the clogging of the motors. But it does. It works pretty slick from a mechanical standpoint. Obviously, we haven't actually been able to fire everything up yet, as the code's not ready yet. But let me give you an overview of how this moves. We've got a Z-axis right here, and this one just rotates the whole machine. We've got, I guess you'd say, a Y-axis back here that tilts it. So it tilts it left to right. It's back there. Then we've got a pretty dense little joint right here that connects this motor, which lifts this first arm segment. And you can see motor 3 rotates this whole segment here. And then we've got motor 4 on the back side here, connected with this linkage to drive this beam up and down with this linkage. Then we've got motor 5 and 6. These are connected with their own linkages to the top panel. They control both the raise and tilt of the panel itself. So altogether, this is a 6-axis arm, essentially, that has quite a bit of freedom. It's pretty flexible, and for being 3D printed, I'm actually pretty pleased with how rigid and durable it is. I mean, it's not rigid, but it's stable. So this is a machine. Some quick overview on the wiring. Obviously, you'll see here's a in the works connector. This is the breakout between the DVI cable and then all of these individual cables to the encoders. So it has to handle not only the SPI communication wires, but it also has to send power to turn on these encoders, which are 14-bit magnetic sensors. They're pretty fancy. They're probably way more accurate than we need on this project, but hey, no reason to go inaccurate. All right, I hope you enjoyed this. It's been a blast for me building this project, and the whole time I've been looking forward to sharing this with you guys and just kind of sharing what I'm excited about, because it's been a hard project. There've been difficulties, but it's been just a blast building this and designing it and bringing it into reality. So yeah, let me know if you like this down in the comments. Leave a like, and hopefully I'll have another video updating you on maybe the software as that comes out. So thanks. Till next time.